Hello, everyone. My name is Guido, and I will be guiding you throughout the wonderful world of Hive, what it is, and how it can be used for many different applications, and how it's currently used for applications such as Facebook and other big data systems. Okay. Many popular industries today face the same problem. We're handling too much data. When it comes to typical warehousing solutions, before Hadoop existed, there were very few methods of maintaining and handling large amounts of datasets from many different customers. With the invention of Hadoop, however, and the invention of the MapReduce algorithm, large businesses and corporations alike have begun to alleviate this issue. Unfortunately, although Hadoop is very strong and effective with handling large amounts of data, it fails to provide an easy-to-use system for the average consumer, due to the fact that Hadoop programs are usually very low-level and require large amounts of maintenance. Hive, a warehouse solution that is built on top of Hadoop, hopes to alleviate this problem. Not only does it use similar SQL patterns, known as HiveQL, but it also supports and maintains a well-structured HDFS system, as well as supports primitive and collective types. In Facebook alone, Hive contains several thousands of tables with over 700 terabytes of data, which are managed by over 100 users at the same time. Hive has allowed Hadoop to become a more structured and easy-to-use system for day-to-day consumers, which is why it is so important in the real world. There are currently many systems that offer SQL-like control over Hadoop databases. One example is Botera Impala. Unlike Hive, Botera Impala does not use MapReduce but instead uses its own executions, which are installed within data nodes. This makes Botera Impala slightly faster than Hive due to that exact reason, but nonetheless, a different file format called Parquet is the only file format supported, which is one of the biggest cons if looking for flexibility. Presto is another alternative created and currently supported by Facebook, who were the original creators of Hive. But just like Impala, although it brings enhanced interactive experience, it suffers from similar issues needing a forced file system known as RC file. More alternatives include Shark, Drill, HawkQ, BigSQL, Phoenix, and Tejo. All of these are great tools that have one purpose in mind: bring SQL to Hadoop. It is to no surprise that such interest has been placed on this goal, as it allows for an easier to maintain and more flexible solution instead of using Hadoop's default data retrieval. However, Hive is one of the de facto tools, and for a reason. It's simple to set up, has a small cost, and it usually does not require a large infrastructure. The Hive database is structured throughout a specific data model and query language. Organized in tables, each table usually corresponds to a single HDFS directory. The data is then serialized and stored within the table, in which the users can manipulate through the same serialization. Given in Hadoop is the capability of creating your own serializing formulas, or you can instead use your own Ploit compression and lazy deserialization formulas. Partition-wise, each table can have one or more partitions that determine the distribution of data within subdirectories. For example, if table T is in the directory /wh/t, a table T with columns ds and ctry can have a particular data with ds 200900101 and ctry us under directory /wh/t/ds/20090101/ctry equals us. Of course, data can also be partitioned into buckets depending on the hash of a column, which can also be helpful if you're adjusting bulk. Hadoop offers primitive column type support such as integers, floating point numbers, strings, and more, but it also allows for the possible definition of your own types, which can be defined programmatically using Java. The query language of Hive is also very beneficial to its users for many reasons. Hive provides an SQL-like query language known as HiveQL, which supports data definition (DDL) statements to create tables with specific serialization formats or column buckets. Loading data is as easy as using load and insert data manipulation statements. Also provided within HiveQL is multi-table insert support and an extensible architecture due to the support of column transformation (UDF) and aggregation (UDAF), which are all implemented in Java. Any custom MapReduce scripts can be implemented within the HiveQL interface as well, so if you have one, you can use it with Hive to achieve customized results. The architecture of Hive also includes different members, namely external interfaces, the thrift server, Metastore, driver, compiler, and execution engine. I will mainly go through a general overview on what these different components do and how they fit together to create the Hive we know today. For external interfaces, users have the ability of using command line, CLI, or web UI, as well as application programming interfaces to access the HiveQL system. JDBC and ODBC are all supported. As for the thrift server, HiveQL provides a framework for cross-language services. This means multiple servers written in different languages can be supported by clients of other languages, which in turn lets many different APIs such as, again, JDBC and ODBC, and scripting languages such as PHP, Perl, and Python to execute HiveQL statements. Versatility is Hive's main priority when it comes to the creation of the thrift server. Moreover, the Metastore contains system catalogs for easy access of the Hive database through traditional relational database methods. This makes simple query executions very fast, but also leads to the issue of keeping the metadata consistent with the HDFS database. The Metastore is also a definite tool when tables are referenced in HiveQL, speeding the process of query generation. Another main architecture module of Hive is the driver, who manages the lifecycle of HiveQL statements. Creating a session handle, the driver keeps statistics such as execution time, number of output rows, and more information about your query to assist the user in maintaining their HiveQL query performances. The compiler invokes the driver upon receiving HiveQL statements and translates each query into a DAG MapReduce plan, while the execution engine submits individual MapReduce jobs in topological order to the system using Hadoop's execution engine. So as you can see, Hive uses the external interfaces, the thrift server, the Metastore, the driver, compiler, and execution engine, all for every query that you submit. In conclusion, Hive has achieved a performance increase over normal Hadoop to around 20%. It is very easy to work with, and it has many different serialization formulas, making manipulation of any kind of data very easy. Hive has many UDF packages and customizable MapReduce functions, allowing a programmer with Python or Perl knowledge to create not only custom scripts but also manipulate the existing MapReduce scripts for customized results. Hive can improve developer productivity due to how HiveQL queries are supported by many statistical processing applications such as rhype, rhive, or rhadoop, and it contains many SQL queries that a relational database user usually knows and understands. Unfortunately, Hive does have its downsides, including poorly execution of simple queries due to its batch nature. However, when it comes to large amounts of data, it outclasses strong database systems like PostgreSQL. Hive is working on improving their SQL support, including columnar storage to improve scan performance, enhancing the existing JDBC and ODBC drivers, and exploring methods of multi-query optimization techniques using n-way joins on a single MapReduce job. Personally, I believe this paper brings about a novel, currently used idea that benefits Hadoop users in many ways. Although Hadoop is a great way of managing big data, it usually requires too much system-level knowledge and programs that are hard to maintain. Using Hive, however, Hadoop database owners can use traditional SQL-like statements to manage their data, and can submit multiple jobs in a very effective way using the Hive structure. Although I will not be using Hadoop for my project, I believe Hive is one of the best possible systems that exist on top of Hadoop to ease the burden of handling large amounts of data. I can definitely see myself using a system such as Hive in the future when I am managing a large database for a well-known or often used company site or application. It was a great and informative read, and it explained very well the steps done to achieve what it does in an easy to understand manner. Thank you for watching, and hopefully you understood Hadoop, Hive, and how it benefits the computer science world and machine learning.